Hi, everyone. Okay, I've been given the green light that I'm good to go. So my name is Mason Lamb. I'm a postdoctoral fellow at the Dunlap Institute at the University of Toronto. And so I'm going to tell you guys today about this technology called adaptive optics, which is kind of at the intersection of astronomy and engineering. And so a little background about where I come from. Um, so I started off in engineering, and I was working as a civil engineer for a construction company doing highway construction. And I was always very interested in stars and in space and astronomy. And then I decided after working for a couple years to just try my hand in astronomy. And so I went to university and did my undergrad. And in my undergrad, I basically found that you could do both astronomy and engineering at the same time. And so what I want to talk to you guys today about is basically how you can, merge the two together and get the best of both worlds. So yeah, I'm going to talk about adaptive optics. Here's an image of a couch that's blurred out, and it's bouncing off of this kind of mirror that can change shape. So I'll talk all about that technology and how it essentially can clear up images of these cool astronomical things we're looking at. Okay, so twinkling stars can be a pain for astronomers. So it turns out that the twinkling stars in the night sky that you're familiar with is comes from a romantic background. So if you're young, this is kind of your first introduction to the night sky. You don't really know about galaxies and exoplanets and stuff like that or planets and other solar systems when you're really young. The first thing you see is the night sky, and you have this kind of awe for the twinkling stars in the sky. And so where this comes from, this kind of romantic aspect to the night sky has even delved into lullabies and stuff. But it turns out to be the bane of astronomers in modern astronomy. The effect that causes stars to twinkle is a huge problem for modern astronomy. And the goal of my talk today is to kind of describe to you how we deal with the process that makes these stars twinkle, and kind of some cool angles and technologies that we use to mitigate this effect, so that you can get the best of both worlds: the twinkling and astronomers that aren't angry. Maybe angry is a strong word. So at the underlying kind of basis of everything is that large telescopes on the ground suffer from the atmosphere. So if you have a star that you're interested in that's really, really, really far away, that star kind of gives off light waves that are coming out in spherical kind of shells. And by the time those light waves reach the Earth, they're more or less like flat and planar. But then when they hit the atmosphere of the Earth, they become distorted and corrugated like a crumpled piece of paper. And so it's that crumpledness to the light wave that causes stars or images of galaxies to become quite distorted. And so we build telescopes both in space and from the ground. And if you had a telescope in space, like the Hubble Space Telescope, and if you imaged or took an image of a nice, pretty star far away, you would get what you see on the left here, where you have this star, but it has these rings. That's just an effect of the telescope itself. It's not super important. Those rings are actually good things, but that's what a perfect star would look like. But on the ground, when you use a big telescope, pretend you put the Hubble Space Telescope onto the ground. What happens is over time, the star breaks up into these little speckles, and the speckles themselves move in a cluster. And in astronomy, we always look at things that are really faint and really far away. So we expose for really long amounts of time. So when you take a long exposure image, it really smears out that speckled star into this big, ugly, blurry blob. So essentially, you would start off with this, the star on the left that has these rings, then that's what you want, but you get this ugly, nasty thing on the right. And so where that really has a visual effect is on things like planets. Here's a picture of Hubble taken from the ground with a normal telescope on the left. And then it's taken also with the Hubble Space Telescope on the right to show you the detail that you get when you get above the atmosphere. So this is the effect that's really impacting astronomers from the ground, and it always has. And so we've long, known that the atmospheres had a really nasty effect on any astronomy that we do. I'm going to tell you guys about how Isaac Newton was actually really smart about it and came up with a cool way that we actually use today to mitigate that. But I really like showing Van Gogh's classic Starry Night painting, where he shows the beautiful stars in the sky and then this kind of swirling, turbulent atmosphere in the same painting. It's kind of cool. It highlights the whole nature of everything we're talking about. But the point of this, the point I'm trying to make is that, we've known that this effect exists for a long time. We've just been stuck with it. And so what I'd like to tell you guys is I'd like to try and motivate why this is happening in the atmosphere so we can get a better understanding, and then to talk about ways that we try and mitigate this. So essentially what's going on in the atmosphere is in turbulent regions, like I'll talk to you guys in a bit about how the jet stream is a particular turbulent region in the atmosphere where the jets travel in. You have mixing of warm pockets of air and cold pockets of air. And so a warm pocket of air will have this, this one index of refraction, which I'll talk about in a second. And a cold pocket of air will have a different index of refraction. And when they mix together, you get this weird distortion. And this is exactly the effect you see when you have a mirage in the desert. You have the earth, which is one temperature, and the air, which is another temperature. And the boundary where they meet, you get the mixing of hot and cold air, and they cause a distortion. When I was talking about different indices of refraction, well, it's just the exact same thing that's going on when you have something immersed in water that appears distorted or different. Water has a different index of refraction than air, and a hot pocket of air has a different index of refraction than a cold pocket of air. So you can see how the popsicle stick becomes distorted in water compared to air. And by the same token, you have fish that appear distorted when they're in the air compared to the water. So that's what's going on in the atmosphere. Basically, in these turbulent regions, you mix these hot and cold pockets of air. So where exactly in the atmosphere do you get this mixing going on? Well, it turns out there's two places. So I don't want to show you something too crazy here, but there's this graph on the left where this axis, the vertical axis, is just height above the Earth in kilometers. And the horizontal axis is the strength of the turbulence, or how much mixing is going on. And this blue curve here shows how much of the turbulence is going on in the atmosphere. And you see a bump at 10 kilometers and a big bump down at what we call the boundary layer. And these are two regions where you get this turbulence happening. And this top portion at 10 kilometers, that's exactly where the jet stream is, where you have this shear between, basically going on between two kind of portions of the atmosphere that causes causes turbulence, which then induces hot and cold pockets of air to mix together. So these are the two main areas we get turbulence that causes the twinkling of stars and that causes these ugly things that happen at telescopes. So one question that arises right away is, should we just stop building telescopes from the ground? So I want to try and highlight to you guys that we should definitely still keep building telescopes from the ground and also build them from space. And I think I can do this. I apologize. I have my 1-year-old in the background. He's going to sleep. But I think that this example I'm going to show you guys kind of highlights why you can't put all your eggs in one basket, why you can't only build telescopes in space. So if you take the Hubble, for example, the Hubble Space Telescope is one of the most amazing telescopes we've ever built. And it's done such a good job over many, many, many years. But it wasn't always that case. When they first sent up the Hubble Space Telescope, instead of seeing that image of a star with all those nice rings I showed you guys, they got the image that you see here on the right. It's all cruddy and distorted. And so it turns out that they had a flawed mirror and they sent this thing up into space. So if they detected this flaw prior to sending this up, it would have been about $2 million to fix. But instead, they sent astronauts who were already going up anyways during the first servicing mission to fix it. But the additional cost was about $85 million. And they installed these special glasses that fixed it. But the point is that, you know, if you're lucky and the telescope's close enough to Earth, you can send astronauts up to fix it. But what happens when you're further away? Once you send that thing up, you can't fix it if there's any problems that go wrong, which we've seen can happen. So this really is highlighted by the next large space telescope, which is the James Webb Space Telescope, or JWST. And so this telescope is going to exist out at this point called L2, a Lagrange point, which is basically, it's kind of like a gravity pocket way out beyond the moon. This shows to scale where the moon is to Earth and where this pocket is that it's going to sit in. So if anything goes wrong when this telescope is out there, you can't really do anything to fix it. So, you know, they know this, and they're taking lots of steps and precautions to make sure that this won't happen. So there's lots of resources in terms of money and time, especially time. And it's just, you know, it's taken a long time to get JWST to the point where it's at now, and it's still, you know, not going up anytime soon. So the point is that, you know, you have to take this into consideration. We really want to try and build them from the ground if we can, because there's another key aspect that I haven't discussed, and that's that size matters. When you increase the diameter of the telescope, you not only increase its ability to resolve or, you know, identify features in objects like galaxies and stuff, but you also increase the light collecting area, and you can look at fainter and fainter and fainter things, or look further out into the galaxy, or you could just be more efficient because you can see, you know, more light. So for reference, the James Webb Space Telescope that I just described, which is the biggest you can do in space, and it's not even out there yet, is shown in this little corner here with its mirror footprint. It's a bunch of hexagons, and it's about 6 meters in diameter. And all of the telescopes here in solid are telescopes that are currently built in existing facilities. And they are all bigger. Most of them are bigger than the James Webb Space Telescope. And then you have the future 30-meter class telescopes, which are massive, and they aren't built yet. You can see that they're faded because they aren't constructed yet. And so you could never really hope to build these massive diameter telescopes out in space. You've got to go on the ground. So, you know, we want to try and build them from the ground. So how do we get past this atmospheric effect? Well, like I said before, Isaac Newton, he's a smart guy. He was onto something 300 years ago. And I just want to show you guys this sample of text from this book he wrote called Optics in 1730. So there's two quotations I want to highlight. The first one is, "For the air through which we look upon the stars is in a perpetual tremor, as may be seen by the tremulous motion of shadows cast from high towers, and by the twinkling of the fixed stars." So, you know, he knew that there was this nasty effect shown by the twinkling of stars, but what he really did that was cool was came up with kind of a proposed solution that actually we use today. And that's in the second quote, where he says, "The only remedy is a most serene and quiet air, such as may perhaps be found on the tops of the highest mountains above the grosser clouds." So he basically said, hey, why don't you get above a lot of this nasty turbulence and build telescopes on top of big mountains? So that's exactly what we do. The biggest telescopes in the world, we build them in places like Mauna Kea in Hawaii or in Chile, where typically you want like a tall mountain, preferably on an island or on a coastal range close to the ocean, where basically you have the situation where undisturbed wind flow develops on the ocean, where you have big open swaths of flat ocean. You have the smooth wind that flows, and then it'll hit like a tall peak, like a mountain. And so, like, say for instance, in Hawaii, if you have, you know, this island that's out in the middle of the Pacific Ocean, all the turbulence develops downstream from this this telescope that's on top of the mountain, and you get this kind of smooth, undisturbed flow that goes over top of it. So this helps helps immensely, and we can get past a lot of the turbulent effects by building telescopes in these remote locations. But you can only do so much. You still have this problem where you have, you know, still the jet stream contributing a large portion of atmospheric distortion. And we want to see, hey, can we basically do as good as telescopes in space? So like I said before, this is what a perfect image of a star would look like in space. And on the right, this is what you see from the ground. And what we can do, it turns out, if we use this special technology, is we can get an image like you see here on the right, where you can see that we make the rings that you want to see. So this is a perfect image of a star. And I think it's even better highlighted if I show you, and this technology, by the way, is called adaptive optics. I should have said that. I'll say that in the next slide. Here's an example of a recent image taken from the ground and showing how it was taken with Hubble and with adaptive optics of Neptune. So on the left is the ground where it's all blurred out, and that's the picture I showed earlier. And then you have Hubble, which can resolve it quite well. But now look at the detail you get from the ground using this technology, using this technique called adaptive optics. You can resolve these crazy fine features. And so this is the ultimate goal of what we want to do: make big telescopes from the ground and make sure that they can give you what you would get in space. So that's the goal of my talk, is to tell you how we do that and what direction we're going in. So how does this all work? How does adaptive optics work? It's actually pretty straightforward. You have this mirror that can change shape. And so that mirror, as I'm showing in this diagram on the right, will intercept this initially distorted light wave, and it'll reflect it, and it will take a portion, a small sample of that light, and send it through what's called a wavefront sensor. And that wavefront sensor will tell you, hey, I know how distorted that light wave is. And it'll tell the mirror to take the opposite shape of that light wave faster than which the atmosphere is changing. Remember, I showed that twinkling star earlier. Well, you just need to do it faster than the star is twinkling. And so it does this in what's called a closed loop, and it does it probably about 1,000 times per second for the average adaptive optics system. If I say AO for the remainder of the talk, it means adaptive optics. So I'll try not to do that, but if I do, that's the situation. So what I'd like to do now is just tell you a little bit about the components that make this system work. So the first major component is that deformable mirror that I told you about. So what shape do we need to take? Well, remember earlier I talked about that star and that light waves when they reach the Earth's atmosphere, nice and flat and smooth, and then they become corrugated and disturbed by the Earth's atmosphere. Well, this is what it actually looks like with an overhead view on the left and a profile view, kind of 3D view on the right. That's what shape the mirror needs to take, or the opposite of that shape, I should say, to make this correction that we need. Okay, so that's what shape we need to make. So how does it do it? Well, it does it with these little tiny pistons, like car pistons or car engine pistons, that are glued to the back of a thin mirror, and the pistons are called actuators. And what I'm showing here is an example of a very stereotypical deformable mirror, which uses magnets that are glued to the back of a thin glass mirror. And the magnets sit inside of what's called a solenoid. And if you apply an electric current to the solenoid, it'll deflect the magnet in and out, causing the mirror to change shape. So this is one of the main technologies. There are others, but this is the one I'm going to talk about today. So that's how you change shape. So then the next question is, okay, how many actuators do we need? Well, the atmosphere, like I showed earlier, causes a star or whatever you're looking at to break up into these speckles. And so if you have a 1 meter telescope, and most amateur telescopes are smaller than 1 meter, you actually don't really break the star up in any speckles. And it turns out you actually don't need really adaptive optics for any small telescopes like that. But as you get to bigger and bigger telescopes, like an 8 meter telescope on the right, which is the size of the current largest telescopes roughly, you get many, many, many speckles that it's broken up into. So as you increase the diameter, you increase the number of speckles, and then you take a long exposure image and you get what we see on the left, but what we want is on the right. So it turns out that you need roughly, very roughly, about as many actuators as there are speckles. I think I can show an example of what's going on with that statement in this slide here, where if you were to take this turbulent picture of what happened to the light wave and show it here in the black curve on the right, what you end up doing is fitting a bunch of piecewise actuators to try and approximate what that light wave looks like. And this is a side profile of the light wave, where each chunk of that actuator is about the size of one of this term we call R naught, which is just a fancy term for speckle. So basically you need about as many actuators as there are speckles. And for typical adaptive optics systems, you need about 500 to 1,000 actuators, depending on the wavelength that you're working in, for good enough correction. Okay, so that's deformable mirrors. The next component that's clutch is the wavefront sensor. So the wavefront sensor is what tells you how distorted the wave is, and what shape you need to essentially send to the deformable mirror. And so if you have the most common one that we use is called a Shack-Hartman wavefront sensor, and it's a grid of lenses. And if you had a nice pristine wave, like I talked about in space and what the Hubble Space Telescope sees, that pristine wave would cause a grid of lenses to focus the light in each of those lenses to these spots in a perfect grid. And that basically is a measurement of what you would optimally want in the best case scenario. And then when you have a distorted or corrugated, crumpled wave, like you do from the atmosphere, it causes those spots to become shifted from their homes, off-centered. And so how far off from the center they are is how distorted the wave is. And you try and essentially tell the deformable mirror to push those spots back to their homes in the middle, and that will correct for the wave. Okay, so how does that process work between the wavefront sensor taking this measurement of a spot and then the deformable mirror saying, hey, I need to make that spot go back to its home, like in this top image here? Well, you basically build a walkie-talkie. So you figure out how the deformable mirror and the wavefront sensor talk to each other by pushing on each actuator of the mirror one by one and measuring what the spot pattern looks like. And you build this kind of relationship and how they talk to each other, and you just store that information. And now any future measurement you take from the atmosphere with this wavefront sensor, you know how to tell the mirror what shape to change to, and you do it, like I said, really fast, like 1,000 times per second. So it works. It works really well. And I want to show you one of the first demonstrations of adaptive optics. This is of a galaxy pretty close by, with and without adaptive optics, taken at the Canada-France-Hawaii telescope. This is taken maybe 20 years ago or more. And it essentially demonstrates this technology that you really get these fine features within the galaxy resolved, where on the left, you just get this blurry, kind of ugly galaxy. And so you'd only get a nice crisp image like you see on the right if you were in space. Okay, so we showed that it worked. But nowadays, we do much cooler things. So here's a cool example. We can use adaptive optics to measure pretty precisely the supermassive black hole in the center of our galaxy, the Milky Way. So how we do that is we take an image of the center of our galaxy, shown in the top here. We use a big telescope like the one, like this one Keck that took this image, which is on Mauna Kea in Hawaii. So on the left is without adaptive optics, and on the right is with adaptive optics. Now, if you take that image over time, and you suppose that you know where you think a big black hole is because you see things like radio emission, all these other signatures, you think there's a black hole there. And if you take many images over the course of like 20 years, it turns out that the stars are moving so fast around that black hole that you can actually measure their movements over time. And you can only do that by using adaptive optics to get the resolved, to resolve these stars, and then to take many measurements over many years to track their motion over time. And what I'm going to show you is a video here where we've done exactly that. This is a group by the European group ESO, where they took data with the very large telescopes, and you can see, zooming in on the center of our galaxy, these are stars measured over time, and you can see 1999, 2000, and you can see the ellipse made as it swings around the black hole. I'm just going to play this again. So these are stars that they observe over time, and they can see them moving really quickly, especially when they get close to where they think the black hole is. And so we can use simple physics, like what we call Kepler's laws, to basically, fit to that ellipse and say, hey, I know what mass a black hole would create an ellipse like that. And so that's a pretty cool use of the technology of adaptive optics. So another crazy thing that I think is just so cool is that we can take direct images of planets in other solar system, and this is solely because of adaptive optics. So what I'm showing here is an actual set of images taken over time, where you can see time again moving from 2009 all the way up to 2016 of planets around a nearby star orbiting around that star, and they blocked out the starlight here in the middle. But you can see the light coming from these planets is actually from those planets. And so they use adaptive optics to get crazy, crazy correction of the atmosphere to really hone in on what's going on around this star. And I'll talk more about how they do that in a second, but you can see the stars orbiting around, the planets orbiting around their star, just like they do in our solar system. And so just to give you an idea of the scale, it says 20 AU is this white bar here. Well, AU, that's an astronomical unit. That's just 1 AU is just the distance between the Earth and the sun. So 20 AU is 20 Earth-Sun distances is the distance between this star and this first planet, just to give you a sense of the scale. So we've done this for many different solar systems now, where we can take direct images of their planets. And this has just opened up a whole world of astronomy. The next thing they want to do is put spectrographs on these planets and see if they can measure what's in the atmosphere. Like, is there water? Is there stuff that may be indicative of life? So that's all possible because of adaptive optics. Now, what's going on? I just really want to quickly show how adaptive optics gives you those planets. So like I said before, adaptive optics off, you have this big, blurry, ugly star, but then you turn it on and you get this really, really crisp image of the star. And then you can use this thing that we call a chronograph, where we essentially block out the light coming from the star itself, but not out of the star where we think planets might be. And you can do some smart post-processing with these images that have adaptive optics correction to tease out where the planets are. So that's what's going on in a nutshell. So finally, I'm going to make a shameless pitch towards the research that I do. I guess I didn't get a chance to say this, but my research is split 50-50 between engineering and astronomy. And so I help build instruments that use adaptive optics, but then I also use them. And so one of the things that we do is we try and hunt for black holes inside of globular clusters. So globular clusters are just big balls, big spherical globs of stars that are some of the oldest things in our galaxy. And there's hundreds of them distributed about, our galaxy, and they're old ancient things. And we think that in the middle of some of these really big globular clusters, there might be black holes. And why that's interesting is we think they might be of a particular size that we've never seen before. We've observed really small, teeny black holes from stars going supernova. And we've observed really massive black holes like what I just described a few slides back. But we've never found the link between the two, between the small black holes and the big ones. And we think this is a way to do it by using adaptive optics to look in detail at the stars inside of this big globular cluster, and then measure the velocity of each of those stars with what we call spectrograph. So how that works is a spectrograph will disperse the light from the star into its rainbow. And the rainbow is made up of a bunch of different colors. Well, each color is at a different wavelength, we call it. And so a nice analogy I like to use is that certain wavelengths give off certain colors. So street lamps, for example, can be made up of sodium, where you excite sodium atoms and they, spit out light at a very specific wavelength, which turns out to be orange. And so you get a spike of light right at that wavelength. Well, by the same token, stars have atmospheres full of elements. And if the light coming from the core of that star passes through its atmosphere, if there's some sort of element like sodium or something else inside of the star's atmosphere, it'll actually absorb that light and take it away before it gets to us. And if you were to show what the spectrum of the star looks like, you'd see these dips like I'm showing here, these little dips in light. And those happen at very specific locations where we know, hey, that's where sodium is, or hey, that's where this element is. And then what we can do is we can measure where that specific dip is with respect to where we think it should be, because what happens is as stars move away from us or towards us, they get what's called red shifted or blue shifted. So if a star is moving really quickly away from us or towards us, it could be really tugged on by a massive black hole that's causing it to have a spike in velocity, and we see its spectral feature move. And the reason why we see the spectral feature move is there's an analogy people often use describing how car sirens, you sound different when they come towards you and when they move away from you. And that's what's called being, the sound waves are being blue shifted and or red shifted and blue shifted. So by the same token, the spectrum, if it moves towards you or if the star is moving towards you, it moves away from you, the dip that you see will either move left or right. So that's how we figure out what the velocity is of these stars. And if there's a spike in velocity in the core, we can say, hey, we think there's a signature for a black hole there. Okay, so enough about the different types of adaptive optics, things we've looked at. We're going to talk about what developments there are in the future, what impact that has on astronomy. Like, where are we going? So there's three main ones I want to talk about that I think are very important. The first is that we're trying to just turn telescopes into adaptive optics systems themselves. Because currently you have a telescope and then you build this adaptive optics instrument that sits in a box with this deformable mirror and this wavefront sensor, and then you just attach that box to the back of the telescope. But what we would really like to do is see if we can just make the telescope an adaptive optics system itself, which has many benefits, and I'll talk about that in a second. And we do it by making the secondary mirror a deformable mirror. So again, I'll talk about more of that in a second. Another cool thing happening in the future is using different flavors of adaptive optics to really push the limits of the science we can do. And a big one for the future is called multi-object adaptive optics, where essentially we're correcting for many different patches on the sky at the same time. So I'll describe in a second how normal adaptive optics only allows you to get one little tiny patch, but what we can do with multi-object adaptive optics is look at a really big field, like a cluster of galaxies, and look at them all at the same time and do some really cool stuff. So we'll talk about that. And finally, I want to talk about how the future of ground-based telescopes is in this kind of regime we call extremely large telescopes. Astronomers aren't super well known for their ability to name things in a reasonable manner. We just say very large telescope or extremely large telescope. But anyways, the future super big telescopes basically have adaptive optics integrated into them at their core. So I want to talk about where we're going in that direction. Okay, so the first thing I'll talk about is the adaptive secondary mirrors. So like I said, make the telescope itself an adaptive optics system. So here's a diagram of the Gemini telescope in Hawaii. And so here's its primary mirror on the bottom, and then it has the secondary mirror on the top. So you essentially, you send light down and it bounces off the primary mirror, and then it hits a secondary mirror and then focuses down to some cool instrument attached on the back of the telescope, whether it's a spectrograph or something that can take images of exoplanets, or if it's an adaptive optics instrument, it all sits inside of a box that fits on the back of the telescope. So what we want to do is let's just, try and kill two birds with one stone and turn that secondary mirror into one that has actuators. So it's a deformable mirror where you've essentially made your telescope an adaptive optics system. And then that will then feed any future instrument. It could be anything. Everything is going to get adaptive optics. And so this is what those things look like. We've started to build them now, and 4 big telescopes have these adaptive secondary mirrors. And they basically are that magnetic actuator deformable mirror technology I told you guys about, where they're little magnets glued to the surface of a thin mirror that sit inside of solenoids, and you apply current to the solenoid and they cause the magnet to move in and out. And so in this case here, there's about 300 of these actuators. And so there's 3 major benefits to doing something like this. One is you've eliminated the need for more mirrors and lenses because they no longer need to exist inside of this adaptive optics instrument. You've made the secondary mirror a deformable mirror. So you've limited the number of lenses and mirrors, and it turns out that each lens and mirror adds contamination to your images in what we call background. And so when you can eliminate more and more background, it makes for better and better images. And another big thing that comes out of this is when you use this technology, you can look at really wide fields of view, we call it. So that's how much of the sky you can look at the same time if you use these adaptive secondary mirrors. And there's a technology I'm going to talk about, this multi-object adaptive optics, that really benefits from this. And the third thing is that when you make the secondary mirror adaptive, like I said, any other instrument now in the back of the telescope can have this adaptive optics correction applied to it, whereas before you had to have a dedicated adaptive optics instrument. So these are really cool, and they're kind of the way of the future. So I thought they would be interesting to share. So the next thing I want to tell you guys about is this technology I touched on, multi-object adaptive optics. So here's a nice diagram I think will highlight what more or less what's going on with the technology. Is that normally when you have some cool, interesting field, like let's say this is a field of the center of a galaxy and there's all sorts of cool stars we're really interested in inside of these white circles. And you need adaptive optics to resolve or to, get the detail you need of those individual stars. So that's your cool target. But it turns out you don't want to steal light from that target to sample with your wavefront sensor to say, hey, how messed up is the atmosphere? You want to steal the light from a nearby star that's really bright, which we call a natural guide star. And so there's kind of a limited region given by this red circle over which you get any reasonable adaptive optics correction. And that's simply because if you go beyond this, you're not sampling the same volume of turbulence in the atmosphere. So you're not applying the right correction to your star. So what multi-object adaptive optics does is it uses these laser guide stars, which is hilarious, but it's actually true. You blast lasers into space and you make fake stars on the sky. And then you can do some tricks, which I'll talk about in a second, how you can now get correction over many different patches on the sky at the same time. Each one of these has a deformable mirror that corrects only this, portion of the atmosphere and then this portion of the atmosphere. So you can look at galaxy clusters, you can look at all sorts of cool stuff. So another shameless pitch, it turns out that we're actually building the very first one of these to be used on a regular basis for a big telescope. It's called GEARMOS, and it's being built at the University of Toronto. And it's going to sit on the back of this telescope. And the principal investigator of this is Suresh Sivanandam. He's a very nice person, very approachable. If you ever have the pleasure of meeting him, I'm sure he will tell you all about this instrument. And it's going to go, like I said, on the Gemini telescope. Probably there's two Gemini telescopes, one in Chile and one on Hawaii. It's probably going to go on the one in Hawaii. And so basically what goes on with this technology is you blast this laser into space to make a fake star so you can sample the turbulence right at that region where the laser is. And you illuminate the sodium layer to make this fake star. And it's about 90 kilometers up. And then so you make, like I said, a constellation, 5 of these stars in our case. And then from the measurements of wavefront sensors of each of these stars, you can reconstruct what the whole volume of the turbulence is in the entire region you're looking at. And you can say, hey, I know the whole 3D model of what the turbulence looks like. I want to apply correction just here, and just here, and just here, and just here. And so that's kind of a key technology for the future that we're going to be using. And we're only just starting to demonstrate it now. And it's really cool. So keep posted for that happening in the next couple of years where we build this instrument that'll do this. Okay, so finally, I'll move on to adaptive optics for extremely large telescopes. So the 3 main big players for ground-based future really large telescopes that'll look in what are called the optical and the infrared regions are called the 30-meter telescope. Its location is still to be determined. The European Extremely Large Telescope, which is in Chile, and the Giant Magellan Telescope, which is in Chile. And so I want to highlight why adaptive optics is so key on these large telescopes. So I think there's a nice analogy I can give you guys, which is if you were to have a loonie and you wanted to be able to distinguish the features on this loonie or see this loonie, we call it resolving. You would need, if you used adaptive optics with the 30-meter telescope, you could resolve or see this loonie all the way from Calgary if this loonie was in Victoria. That just gives you an idea of what type of resolving power you get or how powerful your telescope is if you use adaptive optics. But remember, if you don't use adaptive optics, you just break any image you see, like a loony or whatever it is, up into all these little speckles, and it's not really useful. It just becomes a glorified light bucket. Because remember, I told you guys earlier that when you increase the diameter of telescopes, they do two things. One is they give you better resolution if you have adaptive optics, and the other is they increase the light collecting area. And so that's all you're doing if you don't use adaptive optics, is you just make a massive light bucket. We don't want to spend billions of dollars on these telescopes just to become light buckets. We want to do things like see loonies really far away. Okay, so that's my pitch saying why AO is critical for all future telescopes. And it turns out that these three telescopes that I'm talking about, they have adaptive optics integrated into every aspect of their system. Every instrument will use adaptive optics. It's integrated at its core. And here's a perfect example of one of those telescopes doing this. This is the European Extremely Large Telescope that's going in Chile. And its secondary mirror is an adaptive mirror, just like I described to you guys earlier. So its adaptive optics is incorporated right from the get-go into their entire telescope. It's going to feed all these different instruments. And one of the really cool instruments it's going to feed is called Mosaic. And it turns out Mosaic is this MOA, multi-object adaptive optics technology that I just described a few slides ago. The same technology we're building in Toronto. And so the instrument we're building in Toronto could be thought of as like a demonstrator to help develop this technology so that they can build this thing called Mosaic and ones like this on 30-meter class telescopes. But this is a cool kind of image showing how, hey, you know, advances in adaptive optics happen together. So here's a deformable mirror that's a secondary mirror and this multi-object adaptive optics instrument on the same telescope that's a future 30-meter class telescope. And I think there's one more kind of cool slide I want to share, and that's the Giant Magellan Telescope, that other third large one. Its primary mirrors are a bunch of these dishes like this. And if you're an astute observer, you might be like, those kind of look like what current telescopes are. There's no scale here, so I'm just going to tell you they're exact replicas of current 8-meter class telescope primary mirrors. So they can use the same cookie cutter mold, so to speak, to make these dishes already, to make this super dish using current technology. And their secondary mirror is actually an array of little secondary mirrors, which are identical to current ones on current telescopes. So they're reusing technology we already have. So their secondary mirror is all deformable mirrors. So adaptive optics is integrated into this telescope right from the very beginning. So adaptive optics is here to stay for the future. So I think that's everything I wanted to tell you guys. And what I hope to convey was, one, twinkling stars are neat, but the effect that causes this twinkling makes astronomy very difficult unless we do some smart, tricky things. Two, that space telescopes are awesome, but ground telescopes can also be awesome too, but we have to use things like adaptive optics. Three, that adaptive optics is a really cool technology and it helps us achieve things we could never do before, like take direct images of planets and other solar systems, which is super cool in my opinion. I'm biased though. And that all future large telescopes on the ground will always use adaptive optics. So it's here to stay. So yep, that's everything. And thank you for listening to my presentation, and I'm happy to take any questions. So thanks. Oh, I'm going to look at the questions that are, I guess there's a list of questions that people asked that Kara sent me. Okay, let me read through some of these questions and see if I can answer them right now. Oh, Ben asks, is part of the naming conventions for these telescopes just astronomers one-upping each other? No, I don't think it's something like that. I think it's just, we aren't that, I don't know. I don't want to say we aren't creative, but I think it's just like, it's just that, people will have opinions on what things should be called, but a very safe bet when you have many, many, many people who are part of one telescope is to just name it something simple that everyone understands. So for example, that European Extremely Large Telescope, this might hurt your brain, but at one point it was called the OWL, OWL. and it was the overwhelmingly large telescope. Um, and they cut that name, and I don't think they cut it because they thought the name sounded silly. I think they cut it just because it used to be way bigger, like 60 meters or however big it was. And they cut it down to 40 meters, and they're like, well, it can't be overwhelmingly large right now. It's only extremely large anymore. So I think it's just a matter of, playing it safe. But honestly, I couldn't tell you. The other option is people just name telescopes after people. There's the Keck telescope, the Hubble telescope. There's the Magellan telescope. So that's another safe kind of bet. So yeah, whoops. So that is my answer to that question. Let's see what other questions we got here. Okay, Fretless99 asks, do you believe it to be possible using AO to get a clear image of an exoplanet in the near future? So I think by clear image, you mean like what I showed with Neptune. I think in the near future, no, probably not. I think we'll get clearer images, like maybe we can start seeing maybe signatures of cloud structure, depending on, this is when we're in the 30-meter class era. But I think kind of the holy grail right now isn't so much about getting clear images as it is to get first a really reliable resolved image of the exoplanet, and then to put that light through a spectrograph and to measure the spectrum of the planet's light so that you can find signatures of, water or atmospheric signatures and stuff like that. I think that's kind of the next step. And then maybe in the future, when we have massive telescopes, maybe we can start resolving more structure directly with exoplanets. But I think we're still a ways off from there. Okay, let's see what other questions we got here. the 87. If I wanted to work on designing systems like this, are there any specific companies or organizations to focus on? So there's a couple really cool companies that I think do a really good job of, bridging the gap between industry and academia and also public. One of them's Alpeo. They're a company in France. They do really good work, just in general, making every aspects of the technology involved with adaptive optic systems. So they're a good place to start. Boston Micro Machines makes these deformable mirrors that have crazy high resolution to help us look at these exoplanets. And they, they're a huge competitor in our field. I'm trying to think if there's anyone else. I can't think of any other big companies off the top of my head. There's a lot of questions here. I'm going to see if there's any others I can answer. Margaret asks, can you please explain once again why it's good to build telescopes on coastlines? Well, the coastlines, the only reason why we do it on coastlines is because they're the first mountain range basically in front of the ocean, where the ocean is this, builds up a smooth flow of wind. And if you were to build telescopes on the second or the third mountain range, not on the coastline, you have turbulence that develops from the first couple of mountains that will then hit the telescope and cause the images to be distorted. So what you want to do is build telescopes on that first set of mountains on the coastline so that the smooth air just travels right over top of the telescope, and then the turbulence develops downstream. I hope that answers your question, Margaret. Okay, Super Kya asks, also interested in doing the same thing as you for my career, AO design, 50-50 engineering science, currently doing a master's engineering with some previous astrophysics experience. Any advice? Yeah, I think I could help out there. I actually didn't know that you could do 50-50. I should have explained this further in my introduction, but yeah, I started off in engineering and then decided to do my undergrad in astronomy and saw that you could mix the two together. And then I went off to do my PhD, and they basically gave me the choice, like you could do astronomy only, or you could do engineering only, or you could do both. And so I got to kind of choose my career path there. And so I guess my advice would be is that in your undergrad, you have a lot of, and even if you were doing your master's or if you're completed your master's, if you wanted to go this route, I would consider taking, a master's degree at a university or institution where they have people that work on a bit of both, and doing a small project where there'll be lots of different projects you could work on. I was fortunate enough to be able to see, help build this instrument from beginning to end, and then use this instrument to do science. And that was the 50-50 part of my PhD. But yeah, I think like with anything in life, you just have to, if you really have a strong enough passion for something, you just got to go out and not be afraid to try it. And also don't be afraid to stop doing it if you don't think you like it. That's what I did, but I don't know if that works out for everyone, but that would just be my advice. Okay, let's see what other questions we have here. Oh, is it possible to create the same AO function, deformable mirror, and wavefront sensor on a space telescope? That is asked by Radi. That's a very good question. And people actually do that. But they don't do it to correct the atmosphere, obviously, because you're above the atmosphere. Actually, that's not entirely true. People float balloon telescopes that are above most of the atmosphere, but there's still a little bit left over, and in which case you could use adaptive optics. But I think what people use is they use systems that can measure the wavefront, like a wavefront sensor, to figure out what misalignments there are in a space telescope, and then to have some sort of mechanism. They don't have any deformable mirrors that I know about that will fix this, but other mechanisms to fix the telescope alignment. But telescope alignment is always a problem, and you need to be very careful in space. So this would be a good way to do that. That's a very good question. Okay. Ooh, here's a good question asked by James. How do we know that we got the correct image using adaptive optics? Is there a reference that determines how accurate the images are? So there's two answers to that question. One is that you can cheat by looking at something first with a space telescope to get a rough idea on, what something looks like in pretty good resolution, and then, observe it, follow up with adaptive optics later to get an even better image of it. So that'll give you a ballpark order on how well you do. We actually do that exact approach often. We first use space observations and then follow up from the ground. The other answer is we don't know if we got the I mean, it's kind of hard to get it wrong, because it's kind of hard to get a correct image wrong in adaptive optics. I imagine there are ways, but because it's a closed loop process, you either get the answer wrong and it diverges and it explodes and you have to shut down your adaptive optics system because your deformable mirror is going to try and make some crazy shape, or it converges on a solution. So there's really a right answer or a wrong answer. And if it converges on a solution, you basically always, 99% of the time can say, hey, that looks a little bit better than when we didn't, a little bit better or a lot better than when we didn't use adaptive optics. So that's how you kind of know that you did better than what you started with. I hope that answers your question. Okay, so let's see. What other questions do we have here? So James asks, I am also interested in going into another field after engineering. What would you say the challenges with getting another undergrad degree after engineering is, and how did you overcome them? So one is that one of the challenges is knowing that you're going to be a bit older than the rest of your grad class. So by the time I finished my PhD, I was 31. I think I was 31. So I was a bit older than my peers. But I think at that point, once you're in doing a PhD program, you kind of know if you really like this stuff or not. And you can always, just start off with a master's degree in doing something if you have an interest in it, and, test it out there. So yeah, that was one of the challenges. I think another huge challenge is just trying to not let it weigh on your mind that you made a bad decision, to just really try and trust yourself that, no, this is something I really like and I want to do this. And that's more of a question like a lot of people have in overcoming their own, fears and stuff. Because it's really, people are their own worst critics always. It's really easy to be harsh on yourself. And gaining that confidence that you made the right decision is not easy at all. That's one of the hardest things in life. So for me, I just had to really trust myself, which was a huge kind of, curve for me to learn. That no, I'm doing what I like doing, and then to also be like, you know what, I'm going to keep trying to do this until it doesn't work out anymore, or I'm successful. And if it doesn't work out, I'm not afraid to try other things and to do something else in life. So I think one kind of cool thing about people with astronomy PhDs, they land on their feet pretty well for data science companies. And a lot of my peers have gone off to have very fulfilling careers, working as data scientists. So, there's a lot of decent options. I think you just got to try and not be afraid if you're really keen on this stuff, but it's not for everyone. Ooh, Radi asks, is that how the Hubble's Space Telescope's deformity was found out? Basically, they found it out by, being super excited and, taking the first image on the sky, looking at a star, and they were like all excited, everyone in the control room or whatever. And then they look at the first image and they're like, oh crap, that does not look very good. that's how they found out. Someone could correct me if I'm wrong, but I'm pretty sure that's how they found out. I try to see if there's any other questions, but I think I more or less answered all of them that were asked. Yeah, I think that looks like all the questions. I think we probably, oh, we aren't even run out of time yet. I must have been really quick with my talk. Yeah, sounds like that's everyone's questions. So I really hope you guys enjoyed this talk and, at the very least are interested a little bit more in adaptive optics, and just know that there's a lot of cool things to happen in the future with this technology. So I guess that's bye for now.